Hi, my name is Katrina Jackson, and I am working with Dante Loretta and Yulia Greva of the 9 Circles Research Group, which specializes in experimental plasma chemistry. And we are studying the volatile element compositions of minerals and meteorites. So first I'd like to give you a brief introduction of why we like to study meteorites. Meteorites are so fascinating to study because they are some of the oldest and most pristine materials we have available to us. So studying meteorites can help us learn about the early solar system and how it was formed. So for those of you unfamiliar with meteorites, what we have here are a couple of carbonaceous chondrites and a couple of ordinary chondrites. They are called chondrites because they contain chondrules, which is a small round grains that you see throughout all the samples. And to give you a frame of reference, each of these samples is about a centimeter or two across. So, one interesting aspect about meteorites to study is their composition of volatile elements. Volatility is the ranking of condensation temperatures, and an element's condensation temperature is the temperature at which it condenses into a solid under solar nebula conditions, so namely under low pressure conditions. And so volatile elements are the elements that have relatively low condensation temperatures, and the opposite of volatile is refractory. So refractory elements have relatively high condensation temperatures, and you can see these marked by the blue temperatures and the red temperatures. And you may also notice the different colored boxes standing for lithophile, chalcophile, and siderophile. If you don't know what those words mean, just remember that phile means lover of. So lithophiles are rock-loving elements. They like to form materials like silicates, and chalcophiles are sulfide-loving elements. So for example, you see sulfur, obviously it's a sulfide-loving element. But also other elements such as cadmium and thallium are sulfide-loving elements. And siderophiles are metal-loving elements. So, for example, obviously iron, cobalt, nickel, and copper are metal-loving elements, but also some other ones that maybe you didn't know are metal-loving are rhenium and osmium and iridium. And so, in general, meteorites are depleted in volatile elements, but how much they're depleted depends on where they're formed and about what temperature they're formed. Meteorites generally formed within 1 and 2 AU, so what's now the asteroid belt, but the ones that form within the warmer inner regions of the asteroid belt are more depleted in volatile elements. So, for example, ordinary chondrites are thought to have formed within the inner portion of the asteroid belt, and the ones that formed in the cooler outer regions would have a higher abundance of volatile elements. So, for example, carbonaceous chondrites are thought to form within the outer regions of the asteroid belt. In particular, CI chondrites have very high abundance of volatile elements. And even outside of that, in the very cooler outer regions of the solar nebula, that's where comets tend to form, and comets are very rich in volatile elements. So what we are particularly trying to research is we're trying to find the volatile element compositions of specific metal and sulfide minerals of different meteorite types, and we want to find the fractionation effects between metal and sulfide phases. This picture here is a part of our sample called Ceratov, and you can see there's metal and sulfide solutions right next to each other, so we want to try to find the volatile element compositions in each of these sections to see how it compares. And so how we do this is we have a laser ablation unit coupled with an inductively coupled plasma mass spectrometer. And what the laser ablation unit does is it points a laser at a spot on the sample, and it ablates the spot as small as 10 microns across. And so these vaporized atoms go over to the mass spectrometer, and the spectrometer can count exactly how many atoms of each element you're looking for were in that spot. So you can get very accurate measurements of a very precise spot on the sample. And we use the electron microprobe for preparatory work because that also finds the composition of a small spot on the sample, but you can find more of the major element composition with the microprobe as opposed to the trace element compositions that we're using the laser ablation unit for. And so also the microprobe, it doesn't destroy the spot on the sample while the laser ablation unit does. So of course it makes sense to look through the microprobe first and then get that data to compare with the data you'll get from the laser ablation unit. So what I've been doing so far this semester is a lengthy preparation process, which includes mounting and polishing samples in standards. What we have here is a sample that I mounted and polished. And if you're wondering why the polish looks a bit rough, it's because the rubber polish is better for the laser ablation unit. And also I was told not to tell you that polish is just bad because it's, my first time polishing a sample. And also I've been having to map detailed images of the sample. This is the same sample, and it's put together from about 3 different optical microscope images. And so also analyzing major element compositions of target spots from electron microprobe. Again, this is the same sample, and we looked at 3 different spots on the sample. I'm going to show you these pictures in a bit more detail. You can see here digital camera image placed side by side with an optical microscope image.